imagine for a moment that you are drifting far above the Earth, past the moon, past the bright disk of the sun, out to a place where the stars become a soft scatter of light in every direction. Before we go any further, if you want a brand new space topic every single night to fall asleep to, subscribe. One tap and a new story is waiting for you every evening. From this quiet vantage point, the universe stretches in every direction, and it all seems to follow some hidden order. Galaxies turn in slow spirals. Light bends around heavy things. Tiny particles flicker into being and vanish again, too small to see, yet shaping the world we know. For more than 100 years, the people who study this universe have noticed something strange. The cosmos seems to obey two different sets of rules. One set governs the very large, the planets, the stars, the long curve of space itself. The other set governs the very small, the atoms, the quarks, the soft fizz of particles inside every grain of dust. Both sets work beautifully. Both have been tested again and again, and both somehow refuse to fit together. The first set is called general relativity. It is the theory of gravity that came from the work of Albert Einstein in the early 20th century. It paints gravity not as a pull, but as a gentle shape in space and time. A heavy object like a star makes a soft dent in the fabric around it. Planets roll along that dent. Light leans into it. Time itself slows near it. This idea has been tested by the bending of starlight, by the slow ticking of clocks high above the earth, by the ripples of gravitational waves crossing the cosmos. It has passed every test we have ever given it. The second set is called quantum mechanics. It is the theory of the tiny world. Down at the scale of atoms and smaller, things stop behaving like marbles and start behaving like waves of possibility. A particle can be in many places at once. A measurement nudges reality into one of those places. Energy comes in small steps, not smooth slopes. This theory, too, has been tested with extraordinary care. It built the lasers in your room, the screens on your phone, the long, quiet chains of chemistry that keep your body running. It has never been shown to be wrong. Yet, when you try to bring these two pillars together, something quiet and stubborn happens. The math stops cooperating. Push general relativity down to the scale of a single particle, and the equations start producing infinities. Numbers so large they have no meaning. Push quantum mechanics up to the scale of a whole galaxy, and gravity stops fitting the picture. The two great languages of physics seem to describe the same universe, but they will not speak to each other. This is the heart of the mystery we will sit with tonight. It is the deepest unsolved question in all of modern science. Will physics ever find a single theory, one set of rules, that holds for the very large and the very small at the same time? And if such a theory exists, what would it have to look like to satisfy both of these strange, beautiful descriptions of reality? No one knows. There are many ideas. Some imagine that everything is made of tiny vibrating threads of energy, humming at different notes. Others imagine that space itself is woven from little loops, like a chain mail made of geometry. Some suspect that gravity is not really a basic force at all, but something that emerges from deeper rules, the way the wetness of water emerges from particles that are not themselves wet. Each idea has its quiet supporters. None has been proven. Every one of them faces hard questions that no experiment has yet settled. What makes this mystery so soothing in its own way is that it has been with us for generations. People with brilliant minds have spent their whole lives chasing it. They have filled blackboards, built tunnels under mountains, launched satellites, listened for the faint shiver of waves from colliding black holes. They have come closer, and they have stumbled, and they have begun again. The question is still open. It may be open for a long time. Tonight, you do not need to solve it. You only need to rest with it, to picture those two great pillars standing in the dark, gravity on one side, the quantum world on the other, and the soft, uncertain space between them, where some future theory may one day live. Settle in. Let your breath slow. The universe is in no hurry. Picture, if you can, a single sheet of paper. On it, a few short lines of mathematics, maybe 10 symbols, maybe 20. And inside those few symbols, hidden like a seed inside a fruit, every rule the universe has ever followed. The fall of an apple, the shine of a star, the hum of an atom, slow drift of galaxies through the dark, all of it written in one quiet equation. This is the dream of a final theory. Some call it a theory of everything, though that name has always felt a little too grand. Physicists tend to prefer softer words. A unified theory, a complete framework, a single mathematical language that can describe every force, every particle, every empty stretch of space without breaking down anywhere. The dream is old, older than computers, older than relativity. In a way, it goes back to the first humans who looked up at the night sky and wondered if the same rules that made a stone fall might also guide the wandering lights overhead. The idea that the cosmos is, deep down, one thing, not many things stitched together. One thing. Today, the dream has a sharper shape. It comes down to a particular tension. Modern physics rests on two great pillars, as we touched on a moment ago. One pillar describes the very large. Stars, planets, galaxies, the bending of space by heavy objects. The other pillar describes the very small. Atoms, the particles inside atoms, the flicker of light, the strange behavior of matter when you look closely enough. Each pillar works astonishingly well in its own territory. Together, in the same equation, they refuse to cooperate. A unified theory would be a bridge between the two, a way of writing one set of rules that quietly contains both. When you zoom in, the rules would look quantum. When you zoom out, the rules would look like the smooth, curving space of gravity. And in the in-between places, where the very small meets the very heavy, the equation would not collapse into nonsense. It would keep working. That last part is the hard part. Right now, when scientists try to mix the two pillars, the math often produces infinities. Numbers that should be sensible become endless. Probabilities that should add up to one add up to forever. Something is missing, something deeper. The size of the dream is hard to picture, so let us try. Imagine that the laws of physics are like a map of every road on Earth. The map we have now is detailed in some places and blank in others. We have beautiful, careful charts of the cities. We have rough sketches of the countryside. But there are regions where the ink simply stops. Inside black holes. At the first instant of the Big Bang. At distances so small that our best microscopes would have to be larger than galaxies to see them, a unified theory would fill in those blank regions. It would make the map whole. The strange thing is that nobody knows what such a theory should look like. Some researchers think it will be a theory of tiny vibrating strings, far smaller than any particle. Others think space and time themselves are made of little loops or grains, like sand on a beach you can only see by getting very, very close. Others wonder if gravity is not a fundamental force at all, but something that emerges from deeper rules, the way the wetness of water emerges from molecules that are not themselves wet. We will sit with each of these ideas in turn over the coming hours. For now, the point is simply that the dream has many possible shapes, and we do not yet know which shape, if any, is correct. There is no guarantee the dream can be reached. It is possible the universe has a final answer, and we will find it. It is possible the universe has a final answer, and we will never find it. It is even possible there is no single final answer at all, only deeper and deeper layers, each one truer than the last, but never the last. Physicists disagree quietly and politely about which of these possibilities is most likely. So this is the question we will be wondering about together tonight. Not whether the universe makes sense. It clearly does in its own strange way. But whether the sense it makes can be gathered into a single equation, a single sheet of paper, a single quiet line of mathematics that holds the whole sky inside it. Nobody yet knows. And as you settle in, that not knowing is the soft, open space we are going to wander through. To understand why unifying physics is so hard, we have to go back to the strange birthplace of one of its two pillars. The story begins not in the stars, but in the smallest places we could imagine. It begins in the world of atoms, and in the slow realization that this world plays by rules unlike anything we knew before. Just over a century ago, the picture of matter seemed almost finished. Atoms were tiny, solid things. Light was a wave, smooth and continuous. The universe felt like a great clockwork, ticking forward in steady, predictable beats. Then, quietly, the cracks began to show. A few few odd measurements would not behave. A few glowing materials gave off light in patterns no one could explain. And from these small puzzles, an entirely new world began to open. The first clue came from heat. When a piece of metal glows, it shines in certain colors and not others. The old equations predicted a smooth rainbow that should reach into the deepest blues. But the metal refused. It glowed in soft, limited bands, as if the energy inside it could only come out in small, separate packets. A careful thinker proposed that light itself might travel in these tiny packets, which he called quanta. It was a strange idea at the time. Many hoped it was only a trick of the math. It was not a trick. Soon, more experiments showed that light could behave like a tiny grain and like a smooth wave, depending on how you looked at it. Electrons, the small charged specks inside atoms, did the same. Fired one by one at a narrow pair of slits, they made patterns that only waves should make. Yet each electron arrived as a single dot, like a grain of sand. The very small, it seemed, lived two lives at once. The deeper researchers looked, the stranger the picture became. An electron in an atom did not orbit the center like a planet around a star. Instead, it lived in a cloud of possibilities, a soft fog of where it might be. You could not say where it was until you looked. You could only speak of chances. The act of measuring changed the thing being measured. This was not a flaw in the instruments. It seemed to be how the world truly worked at that scale. From these clues, quantum mechanics slowly took shape during the early decades of the 20th century. It was not the work of one mind. It grew through letters, arguments, late nights, and quiet corrections. Some of the founders were uneasy with what they had built. One of them famously refused to believe the universe could play dice with itself. He spent the rest of his life looking for a deeper layer beneath the randomness. He never found it. The randomness so far has held. What made quantum theory so powerful was also what made it so disturbing. It worked. Its predictions, tested again and again, matched the world to astonishing precision. The colors of glowing gases, the way metals conduct electricity, the behavior of light in a crystal, the structure of every atom in your body, all of it followed the new rules, and yet no one could quite say what the rules meant. The math gave answers without telling a clear story. Some thinkers believed the strangeness was only on the surface. They imagined hidden variables, secret levers behind the curtain that would restore a calm and certain world. Others wondered if the universe truly splits into many versions every time a measurement is made, each version equally real. A third group held that the question itself was wrong, and that we should simply use the math and stop asking what lay beneath. These views still live side by side today. The argument never fully ended. It only grew quieter while the equations kept working. This is the soil from which one half of modern physics grew. A field built on probability instead of certainty. A field where particles are also waves, and waves are also particles, and the act of looking shapes the answer. It explains the inner life of matter with breathtaking accuracy. And yet, it has never been comfortable with gravity, the soft pull that shapes the worlds of the very large. That tension between the foggy world of the small and the smooth world of the large is the central knot we are slowly trying to untie. Tonight, we are simply visiting the place where the small world began. A strange place, a quiet place, a place built from clues, hunches, and equations that still keep some of their secrets. The very small, it seems, was only the first surprise. If the quantum world is the realm of the small, then general relativity is the language of the large. And the large, it turns out, is built from the same patient ingredients as the small, just arranged across distances the mind can barely hold. Tonight, let us drift outward, away from the buzz of particles, and into the slow architecture of stars, planets, and the long, quiet roads between them. Consider, for a moment, the iron at the center of the earth, a great hot ball of it, spinning slowly beneath our feet, generating the magnetic field that wraps our planet in a soft, invisible shield. That iron did not begin here. It was made inside an older star, somewhere else, long before the sun was born. Stars are slow furnaces. They fuse light elements into heavier ones across millions of years, pressing hydrogen into helium, helium into carbon, carbon into oxygen, on until they reach iron. And when certain massive stars finally collapse, they scatter those heavy seeds back into the dark, where new clouds gather and new worlds begin. Almost everything solid you have ever touched is, in this sense, the dust of a dead star. The calcium in your bones, the oxygen you breathe, the silicon in stone, all of it cooked in some ancient furnace and then released into the cold, drifting for ages before settling into the body of a planet. Einstein's equations describe how those drifting clouds curve the space around them, how they pull together, how they spin and flatten into disks, how they finally ignite into new suns. The very large is governed by gravity, and gravity, for now, lives in a different mathematical home than the particles being shuffled around inside it. The oceans hold their own quiet puzzle. Where did all this water come from? One idea is that comets, those icy travelers from the outer edges of the solar system, delivered much of it during the chaotic early years of Earth. Another suggests that water was already locked inside the rocky grains that built the planet, and it slowly worked its way to the surface as the young world cooled. The truth is probably a mixture of both, but the exact balance remains an open question. Researchers compare the isotopes of hydrogen in comet ice to the isotopes in Earth's oceans, looking for a match, and the answers so far are partial, suggestive, incomplete. Even the gases of our sky carry distant origins. Nitrogen, which makes up most of the air, was forged in the cores of stars and ferried here in the gravitational pull of a forming Earth. The carbon in every leaf, every breath, every living cell was once a fleck of stellar ash, and the patterns by which all this matter clumps into galaxies, sheets, and filaments across the universe are described at the largest scales by the gentle geometry of general relativity, where space itself bends under the weight of what it carries. Here is where the tension begins to ache. The small things, the atoms and quarks that make a star possible, obey the strange probabilistic rules of quantum mechanics. The large structures those atoms build, the stars and galaxies and clusters of galaxies, obey the smooth, curving rules of general relativity. The two descriptions almost never meet. A planet is too large to behave like a quantum particle. A quark is too small to noticeably bend space. So for most of the universe, physicists can use one set of rules or the other, and the awkwardness stays politely hidden. But every grain of sand on a beach is, in some sense, a meeting place. Inside it, quantum rules govern the dance of electrons. Outside it, gravity holds it to the earth. The grain itself is the seam. We simply do not yet have a language that describes both sides of that seam in a single breath. Some researchers believe the seam is an illusion, that one side will eventually dissolve into the other. Others suspect the seam is real, and that the universe is woven from two genuinely different kinds of thread that we have not yet learned to braid. So as you settle into stillness tonight, picture the slow links that hold the very large together. The iron in the Earth's core, glowing red from the heat of its birth. The water in the oceans, perhaps carried here on quiet comets. The air drawn in and out of your lungs, made of atoms older than the sun, all of it bound by gravity into the soft curving shape of space, and all of it, somehow, also made of the restless quantum stuff we met in the last section. How those two truths fit together is the question that follows us into every section to come. Among the four known forces of nature, gravity is the strange one. It pulls planets into their slow orbits, gathers gas into stars, and curves the path of light around heavy things. It built the galaxies, and it holds your body to the floor while you rest. And yet, when we try to fit gravity into the same picture as the other forces, something quietly refuses to line up. The other three forces all share a kind of family resemblance. They live inside the framework of quantum theory, where the world comes in tiny packets called particles. The strong force, the weak force, and the electromagnetic force all behave like this. Each one is carried by little messenger particles that hop between bits of matter, pushing and pulling at the smallest scales. Physicists have learned to describe these three with great care, using equations that match the lab again and again. Gravity does not behave that way, at least not in any picture we have made work. In our best theory of it, gravity is not a force passed between particles. It is the shape of space and time itself. A heavy object bends the space around it, like a stone resting on a soft cloth. Other things move along that curve, and we feel that motion as a pull. This is the language of general relativity, and it is smooth, gentle, and continuous. So we have two ways of speaking about the world. One language uses tiny jumps and packets and probabilities. The other uses smooth curves and flowing geometry. Both work beautifully in their own domains. Both have been tested for a century, and neither one knows how to speak the other's tongue. There is another oddity about gravity, one that makes it feel even more like an outsider. Compared to the other forces, gravity is unbelievably weak. A small magnet can lift a paperclip off the floor, beating the gravity of the entire Earth in a single tug. The strong force inside an atomic nucleus is stronger still, by numbers so large they are hard to picture. Why is gravity so faint when its reach is so vast? No one knows for sure. Some researchers wonder if part of gravity's strength leaks away into dimensions we cannot see. Others suspect that the weakness is just a brute fact of our universe, with no deeper reason behind it. Gravity is also the only force that pulls on everything without exception. Light feels it. Empty space feels it. Even time itself bends under it, ticking a little slower near heavy objects than far from them. A clock at the bottom of a mountain runs at a slightly different pace than a clock at the summit. This has been measured carefully and many times. It is a small effect in daily life, but it is real, and it tells us that gravity is woven into the very fabric of when and where. You can begin to see why bringing gravity into the quantum fold is so hard. The other forces act on a stage. Gravity is the stage. To make a quantum theory of gravity, we would have to quantize the stage itself, breaking smooth space and smooth time into something grainier, something countable. And we do not yet know if reality allows this, or what such grains might look like. One idea is that space, at the smallest scales, is made of tiny loops or threads, woven together like a chain mail of geometry. Another idea pictures space as built from countless little events, stitched into a kind of evolving network. Still another suggests that gravity is not fundamental at all, but emerges from something deeper, the way the warmth of a room emerges from the rushing of unseen molecules. Each picture has its supporters. Each picture also has gaps no one has yet filled. What unites these guesses is the suspicion that gravity is trying to tell us something. Its weakness, its smoothness, its strange habit of bending time may all be clues. Perhaps the reason gravity will not join the quantum family is that we have been asking it the wrong question. Perhaps we have been treating it as a force when it is really a side effect of something more basic, something we have not yet learned to name. For tonight, it is enough to picture gravity as the quiet outlier, the patient sculptor of galaxies, the gentle slope that pulled the first dust into the first stars and shaped the long, slow arc of cosmic history. We feel its presence in every step and every falling leaf. And still, after centuries of study, we cannot quite say what it truly is. The mystery sits in the room with us, calm and steady, waiting. Of all the forces in nature, the strong force may be the strangest. It holds the inside of every atom together. Without it, nothing solid would exist. And yet, for all its importance, it works only across a distance so tiny that no human eye, no microscope, no instrument of ordinary life will ever see it directly. To feel how small this scale is, picture a single grain of sand resting on your fingertip. Inside that grain sit countless atoms. Each atom is mostly empty space. At the center of each atom lies a nucleus, a tight little knot of protons and neutrons. And inside each of those protons and neutrons sit even smaller things called quarks, bound together by the strong force. If you blew a single proton up to the size of a baseball stadium, the quarks inside would still be smaller than gnats drifting above the field. The strong force is the invisible glue that keeps those gnats locked in place. And its reach is so short that beyond the width of a proton itself, it fades away to almost nothing. It is a force of the extremely close, the unbelievably near. Try a different picture. Imagine you shrunk yourself down until a single atom looked as large as a cathedral. The nucleus at the center where the strong force rules, would still be no bigger than a grain of salt resting on the cathedral floor. The rest of the cathedral would be empty space, humming with the faint blur of electrons. Almost all the mass of that atom would sit inside that tiny grain. Now zoom in further. Inside that grain of salt, the quarks would dance and twitch on a scale so small that you would need to magnify it another 10,000 times to begin to see them. The strong force lives in that final, hidden basement of reality. It is the smallest neighborhood where physics still has clear rules. And here is where its strangeness shows. Most forces grow weaker as things move apart. Pull two magnets away from each other, and the pull fades. Drift away from Earth, and gravity loosens. But the strong force does the opposite. Try to pull two quarks apart, and the force between them grows stronger, like a stretched rubber band. Pull hard enough, and the band does not snap into freedom. Instead, the energy you put in creates new quarks, and you end up with two pairs where there was one. The quarks refuse to be alone. No one has ever seen a single quark drifting by itself. This odd behavior has a name. Physicists call it confinement. And confinement is one of the deep, open puzzles in the story of unification. We can describe the strong force with beautiful equations. We can predict many of its results. But proving from first principles why quarks must always stay bound, why nature locks them away from solitude, remains an unsolved problem. Some of the world's sharpest minds have spent decades on it. A formal proof carries a $1 million prize, still unclaimed. The strong force also carries a strange kind of weight. Most of the mass of everything you have ever touched, your hand, your blanket, the walls of your room, does not come from the quarks themselves. The quarks are nearly weightless. Most of the mass comes from the energy of the strong force binding them together. In a sense, the solid feel of the world is mostly trapped motion. The chair beneath you is mostly empty space filled with humming force. Set this against gravity for a moment. Gravity reaches across billions of light years, gentle but endless. The strong force reaches no further than a whisker on a proton. Yet it is, at that scale, around 100 trillion times stronger than gravity. Two forces, two opposite personalities, one vast and faint, one tiny and ferocious, and somewhere, perhaps, a single deeper rule that gives birth to both. That is the dream of unification. To find the hidden grammar that makes the strong force and gravity two dialects of one cosmic language. Some theories try to weave them together through strings, others through loops, others through symmetries that have not yet shown themselves in any experiment. None has yet succeeded. The strong force, for now, sits inside its tiny kingdom, doing its strange work, refusing to surrender its secrets easily. And so tonight, as you rest, consider that every atom in your body is held together by something we still do not fully understand. A force so small in reach, so vast in strength, so faithful in its work that the matter of you stays the matter of you. Quietly, reliably, across a lifetime, across all the lifetimes that have come before. Picture, if you can, the inside of an atom. Not the cartoon version with neat little balls in orbit, but something far stranger and more empty. A nucleus sits at the center, a tight knot of protons and neutrons, and around it, vast halls of mostly nothing. If you could shrink yourself down to float inside this hidden chamber, you would see almost no solid thing at all. Only fields, only soft glows of probability, only the faint, restless shimmer of particles that are not quite particles. Now imagine drifting closer to one of those neutrons. From a distance, it looks calm. A small gray sphere, perhaps content in its place. But if you waited long enough, and if that neutron were alone, free from the company of a nucleus, something quiet would happen. After about 15 minutes, on average, the neutron would simply change. It would let go of what it was and become something else. A proton would appear in its place, and with it, two faint travelers, an electron, and a tiny, almost weightless thing called a neutrino, slipping away into the dark. This is the work of the weak force. And if you tried to picture its surface, its texture, you would find it almost impossible to draw. The strong force, as we saw, has a kind of clenched, springy presence, holding quarks in tight bundles. The weak force has no such grip. Its character is one of slow change, of patient transformation. It does not bind things together. It rewrites them, one quiet event at a time. If the strong force is the muscle of the nucleus, the weak force is something closer to a slow tide. It works at distances so small that even on the scale of a single proton, it feels short of reach. Its range is thought to be about 1,000th the width of a proton. So small that it almost does not exist beyond the particle it touches. And yet, without it, the sun would not shine. The first step in the long chain of reactions that powers our star depends on the weak force. A proton becomes a neutron deep in the solar core, and from that single quiet transformation, the rest of fusion can begin. Picture then this surface you cannot really see, a faint, flickering film that lives only at the very skin of a particle. Imagine it the color of dim copper, or the soft violet of a deep twilight, depending on your mood. Imagine it as a slow, breathing thing, where now and then a quark inside a neutron size and shifts its identity, and the whole structure follows. The neutron becomes a proton, and an electron drifts out, and a neutrino escapes through the walls of the atom as though those walls were never there. Because that is the other strangeness of the weak force. Its messengers, when they appear, are extraordinarily heavy. The strong force is carried by tiny massless gluons. The electromagnetic force is carried by massless photons. But the weak force is carried by particles called the W and Z bosons, and they are nearly 100 times heavier than a proton. They flicker into existence for only the briefest instant, do their quiet work, and vanish again before anything can notice. This is why the force feels so faint, so slow, so short in reach. Its carriers can barely afford to exist. For a long time, physicists wondered why this force was so different from the others. Why so weak? Why so slow? Why its messengers had such enormous mass, while the photons of light have none at all? One answer, which has held up well in experiments, is that the weak force and electromagnetism are really two sides of one deeper force, separated by something called the Higgs field. We will come back to that field later. For now, it is enough to know that some of the strangeness of the weak force may be a kind of illusion, a difference that only shows up at the temperatures and energies of our cool, settled universe. But other questions stay open. Why does the weak force prefer one-handedness of particle over another, breaking a symmetry the other forces obey? Why is it so deeply tied to the strange mismatch between matter and antimatter in the cosmos? Some researchers wonder if the weak force holds clues to why anything exists at all. Others suspect its quirks are simply leftover details from an earlier, hotter age. The surface of this force shimmers with hints, and we still cannot quite read them. So we sit with the weak force tonight, this gentle rewriter of matter, and we let its slow patience settle over us. To understand why the search for one grand equation feels so possible, and at the same time so out of reach, it helps to look back at a moment when two very different forces became one. For most of human history, light and magnetism seemed like separate things. Light was the warm glow of a candle, the silver shimmer of the moon, the colors that spilled through a glass of water. Magnetism was the quiet pull of a lodestone, the way certain rocks tugged at iron filings, the strange compass needle that always pointed north. Nobody guessed they were two faces of the same thing. The story of how they came together is one of the gentlest mysteries in science. In the early 1800s, careful experimenters noticed that a wire carrying electric current could nudge a compass needle. Move the current, and the needle moved. A magnet, in turn, could push electric charges through a wire if you waved it nearby. Electricity and magnetism, it seemed, were whispering to each other across some invisible bridge. But no one yet knew the shape of that bridge, or how deep it ran. The answer came from a Scottish thinker who spent years writing equations at a quiet desk. He worked out a small set of formulas that described every known electric and magnetic effect at once. And then he noticed something astonishing buried inside his own math. The equations predicted a wave, a ripple of electric and magnetic fields weaving around each other, traveling through empty space. When he calculated the speed of that ripple, it matched the speed of light almost exactly. Light, it turned out, was an electromagnetic wave. Three different things, electricity, magnetism, and light, were really one thing wearing three different masks. This was the first true unification in physics, and it changed the way scientists thought about the world. If two forces that seemed so unalike could turn out to be the same force underneath, then perhaps every force in nature was hiding a similar secret. Perhaps gravity and the strong force inside atoms and the weak force that ruled radioactive decay were all branches of one deeper tree. The dream of a single equation, the one we have been wandering toward all night, was born in that quiet moment with a compass and a wire. What made the unification so beautiful was that it did not just stitch two ideas together. It revealed something new. The equations predicted radio waves long before anyone built a radio. They predicted microwaves, infrared, ultraviolet, X-rays. All of these are the same kind of wave as visible light, just stretched longer or squeezed shorter. A whole hidden spectrum opened up beneath the surface of the world, and we had been swimming in it without knowing. The lesson was simple and a little humbling. The world we see with our eyes is only a thin slice of what is really there. Beneath the surface of ordinary things, deeper patterns connect what looks separate. The candle flame and the magnet on the refrigerator door are speaking the same language. We just could not hear it until the math was written down. Physicists carried this lesson forward into the 20th century. They wondered whether the weak force and electromagnetism might also be one thing in disguise. After many years, the answer came back yes. At very high energies, the kind found in the first fractions of a second after the universe began, those two forces blur into a single unified force called the electroweak force. Another mask had fallen. Another bridge had been crossed. And so the question naturally grows. If electricity, magnetism, light, and the weak force are all branches of the same hidden tree, why should gravity be different? Why should the strong force stand apart? The history of unification has been a slow, patient revealing of sameness beneath difference. The hope is that the pattern continues. The worry is that it might not. Some thinkers believe gravity will eventually fall into line, joining the other forces in one elegant equation. Others suspect that gravity is something stranger, not a force at all in the usual sense, but a kind of side effect of something deeper we have not yet named. The first view is the dream of unification. The second view is the dream of emergence. Both are taken seriously. Neither has been proven. What remains certain is only this: the world has surprised us before by showing that separate things were secretly one. It may surprise us again, or it may, this time, hold something back. For now, the equations Maxwell wrote still hum beneath every screen, every signal, every beam of starlight. They are a quiet reminder that unification has happened. Whether it can happen again, all the way down to gravity itself, is the question we keep turning over in the dark. Over the last 100 years, physics has built one of the great structures of human thought. It is called the Standard Model, and it is a kind of map of the very small. It lists the particles that make up matter and the forces that act between them. It tells us how quarks bind into protons, how electrons orbit nuclei, how light is born and absorbed. For decades now, every careful experiment has agreed with its predictions, sometimes to 10 or 12 decimal places. And yet, when physicists describe it, they often sound a little uneasy. The Standard Model works beautifully, but it feels unfinished. It hums along like a great clock, ticking through cycles of creation and decay, and still there are gaps in the gears, pieces missing, numbers that seem to come from nowhere, questions the model itself cannot answer. Think of the particles it describes as moving through a quiet rhythm. Quarks combine into protons and neutrons. Those bind into nuclei. Electrons settle around them. Atoms come together into molecules, into stars, into us. Each step follows rules the Standard Model lays down precisely, and yet the rules have a strange shape. There are exactly 3 families of matter particles, each heavier than the last, and no one knows why there are 3. Not 2, not 7, 3. The first family makes up nearly everything around you. The second and third families show up briefly in particle collisions, then decay away in tiny fractions of a second, like notes that sound and vanish. They seem almost unnecessary. The universe could, in principle, run on the first family alone. Why nature bothers to produce these heavier echoes, no one can say. One idea is that the pattern hints at some deeper symmetry hidden beneath the model, a structure we have not yet uncovered. Another view is that the three families are simply a brute fact, written into the universe with no reason behind them at all. The question stays open. There are other gaps as well. The standard model has around 19 numbers that must be measured by hand and then plugged in. The mass of the electron, the strength of the weak force, the mixing angles between quark types. The model does not predict these values. It only accepts them. Some physicists find this troubling, as if the equations were a beautiful song with the lyrics missing. Others suspect that a deeper theory, still hidden, would explain why these numbers take the values they do. For now, we simply write them down and move on. Then there is the matter of what the model leaves out entirely. Gravity is not in it. The curving of space, the falling of apples, the orbits of moons, none of that appears in the standard model at all. Dark matter, which seems to outweigh ordinary matter by a factor of 5, is missing. Dark energy, which seems to push the cosmos apart, is missing. Neutrinos, those ghostly particles that drift through stars and stone alike, were once thought to be massless in the model. Experiments later showed they do have tiny masses, and the model had to be patched to account for it. So the rhythm of physics has been strange. A discovery confirms the model. Then a measurement reveals something it cannot explain. Then another confirmation. Then another quiet anomaly. The cycle repeats. The standard model breathes in successes and breathes out new mysteries. And the larger question, how to unify it with gravity, how to complete it, remains unanswered. Some researchers wonder if the missing pieces all point in the same direction. Perhaps dark matter, the neutrino masses, the three families, and the unexplained numbers are clues to a single deeper theory. Perhaps a grand unification waits beyond, in which the forces we see as separate are revealed as different faces of one force. Other physicists are more cautious. They suggest that the gaps may have separate causes, that there is no single hidden pattern waiting to be found, only a patchwork of small explanations to be discovered one by one. We do not know which view is right. The experiments continue. Detectors buried in mountains watch for dark matter that may never arrive. Underground tanks count neutrinos passing through the Earth. Accelerators smash particles together at energies that would have seemed unimaginable a century ago. Each result narrows the possibilities a little. None has yet shown us the shape of what lies beneath. The standard model, for all its precision, may be a doorway rather than a destination. Behind it, something larger may be turning slowly, patiently. We have not yet seen its full face. We only catch, now and then, the soft outline of something we do not understand. Nothing in the universe stands truly alone. Every particle drifts inside a web of fields, and those fields press in on each other in ways we are only beginning to understand. To ask why a thing has mass is to ask what surrounds it. And the answer, as far as we can tell, is something invisible that fills all of space. A quiet neighbor we cannot see, but whose presence shapes the weight of everything. We call it the Higgs field. It was first proposed in the 1960s when several physicists working in different rooms in different countries arrived at a similar idea. They were trying to solve a small but stubborn problem inside the equations of particle physics. The math worked beautifully if the basic particles had no mass at all. But the real particles do have mass. Electrons have mass. Quarks have mass. Something had to explain the gap between the clean equations and the heavier reality. Their idea was strange and lovely. They suggested that space is not empty in the way we usually picture it. Instead, a soft, steady field hangs over every cubic inch of the cosmos, and particles gain their mass by moving through it. Think of it as a kind of cosmic syrup, though even that picture is a little too thick. Some particles feel the field strongly and become heavy. Some barely notice it and remain light. Some, like photons, pass through without any drag at all. For decades, this remained a beautiful guess. The field was invisible. Its effects were everywhere and nowhere. To prove it existed, physicists would need to disturb it, to ring it like a bell and listen for the tone. That tone would be a particle, the Higgs boson, a brief ripple in the field itself. And rippling such a field would require energies far beyond ordinary experiments. The Large Hadron Collider, a ring buried beneath the border of France and Switzerland, finally reached those energies. In 2012, two separate teams announced that they had found a new particle whose properties matched what the Higgs boson should look like. The field, it seemed, was real. The quiet neighbor had answered. The discovery confirmed one of the deepest predictions of the Standard Model, and yet, in confirming it, the Higgs also opened new questions that have not gone away. The mass of the Higgs boson itself, when measured, sits at a value that physicists find puzzling. It is much lighter than many calculations suggest it should be. Some quantum corrections, when added together, ought to push its mass to enormous numbers. They do not. Something seems to be holding it down. We do not yet know what. One proposed answer was supersymmetry, the idea that every known particle has a heavier partner, and that these partners would cancel out the troublesome corrections. The math is elegant. The predictions were clear. The colliders looked. So far, no partners have appeared. This silence is itself a kind of clue, though no one is sure how to read it. Some researchers still believe supersymmetry exists at energies we have not yet reached. Others wonder if the principle behind it was simply wrong. Another possibility is that the universe is finely tuned in ways we do not fully grasp. Perhaps the Higgs mass is light because, in some larger ensemble of possible universes, only the light ones allow stars and atoms to form. This is sometimes called an anthropic argument. It does not satisfy everyone. To many physicists, it feels less like an answer and more like a shrug. The Higgs also leaves gravity untouched. The field gives mass to particles, but mass and gravity are not the same conversation. A particle gains its inertia from the Higgs. How that inertia then bends space-time is a separate puzzle that the Standard Model does not address. The Higgs is a piece of the picture, not the whole picture. It tells us why an electron resists being pushed. It does not tell us why the electron falls. So we are left with a strange portrait. Empty space is not empty. A soft field hums everywhere, giving heft to the world. We have heard its faintest note in one of the largest machines ever built. And still the question of why that field has the strength it does, and how it fits into a deeper theory that includes gravity, sits open on the table. The neighbors of any particle, it turns out, are not just other particles. They are fields, layered upon fields, each one quietly shaping what the others can do. Somewhere within those layers, the unification we are searching for may be hiding. Or it may require a layer we have not yet imagined. When physicists try to push their best equations to the most extreme places in nature, something strange happens. The numbers stop behaving. They climb and climb, and then they refuse to stop climbing at all. They reach for infinity, and infinity, in the language of physics, is almost always a sign that something has gone wrong. This is the deepest trouble in the search for a unified theory. At the center of a black hole, where matter is crushed into a point, general relativity predicts that the density becomes infinite. The curvature of space becomes infinite. Time itself seems to end. At the very first moment of the Big Bang, the same thing happens. Run the equations backward, and the entire universe collapses to a point of infinite heat, infinite density, infinite curvature. Nature does not seem to like infinities. Most physicists suspect that these blow-ups are not real features of the cosmos. They are signs that our equations have stopped working. The way a map shows a blank space where the cartographer ran out of knowledge. Quantum mechanics has its own troubles with infinity. When physicists first tried to calculate how an electron interacts with its own electric field, the answer came out infinite. The little particle, surrounded by its own influence, seemed to carry an unlimited energy with it everywhere it went. For years, this looked like a fatal flaw. Then a clever idea emerged, called renormalization. The trick was to subtract one infinity from another in a careful, controlled way, leaving a finite answer behind that matched experiments to astonishing precision. It worked. It still works. But many physicists, including some of its inventors, never quite trusted it. They felt the math had been bandaged rather than healed. For the other forces in the standard model, this bandaging holds up. The strong force, the weak force, electromagnetism, all of them can be tamed by renormalization, their infinities absorbed and hidden. Gravity refuses. When physicists try to treat gravity the same way, as a quantum field carried by tiny particles called gravitons, the infinities multiply faster than they can be removed. Each correction brings new blow-ups. The equations demand an endless list of adjustments, and the predictive power drains away. Gravity, in this language, is what physicists call non-renormalizable. It will not sit still long enough to be tamed. This is the heart of the extreme problem. The very places where gravity and the quantum world must meet, the centers of black holes, the first instant of time, distances smaller than any we can imagine, are exactly the places where both theories give answers that cannot be true. The smallest length we can sensibly speak about is called the Planck length, around 100 million trillion times smaller than an atom. Below this scale, the smooth fabric of space described by Einstein may dissolve into something else entirely. The smoothest sheet, looked at closely enough, may turn out to be made of foam or threads or something stranger still. Nobody knows. Theories of unification take different positions on these infinities. Some, like string theory, propose that particles are not points at all, but tiny vibrating strands. By spreading the particle out, even by a hair, the infinities soften. The blow-ups vanish, replaced by finite, well-behaved numbers. Other approaches, like asymptotic safety, suggest that gravity might tame itself at very high energies. The force would approach a fixed, finite strength rather than running off to infinity, like a river that finds its natural depth. A third family of ideas loop quantum gravity among them, proposes that space itself is grainy at the smallest scales, woven from indivisible units. If space cannot be divided forever, then nothing inside it can either, and the infinities lose their place to hide. Each of these proposals trades one mystery for another. String theory needs extra dimensions of space that no one has ever seen. Asymptotic safety needs a fixed point in the equations that has only been hinted at, never proven. loop quantum gravity needs a careful explanation of how smooth, ordinary space emerges from a fundamentally grainy world. No experiment has yet picked a winner. The energies required to probe the Planck scale directly are billions of times beyond any machine humans have ever built, or perhaps ever could build. So the infinities sit there, waiting. They sit at the heart of every black hole in the sky tonight, hidden behind their horizons. They sit at the beginning of time, in the moment before the equations could speak. They are the loud signal that something deeper is still missing. The trouble with infinities is not really a trouble with numbers. It is a quiet message from the universe, telling us we have not yet learned its true language. Somewhere beneath the smallest things we know, there may be something even smaller. Not a particle, not a point, something more like a tiny vibration. This is the soft, strange idea at the heart of string theory. And though we have never seen these strings, the picture they paint is so quiet and so detailed that many physicists have spent their lives listening for them. The idea began in a curious way. In the late 1960s, researchers were trying to understand the strong force, the glue that holds the centers of atoms together. The math they were playing with happened to describe little vibrating threads. The model did not quite work for what they wanted, but the math itself was beautiful, and a few people kept turning it over in their hands, the way you might keep a smooth stone in your pocket. What they noticed was this: if you imagine the fundamental things in the universe not as tiny dots, but as tiny loops or lines of energy, vibrating at different rates, then the different notes those strings play might be the different particles we see. An electron would be one note, a quark would be another, a photon, the carrier of light, would be yet another. The whole zoo of particles would become, in this picture, a kind of music. It is a soft and lovely thought. The universe humming to itself on a scale so small that no microscope we have built could ever see it. The strings, if they are there, would be unimaginably tiny, far smaller than a proton, far smaller than the smallest distance we can probe today. We are, in a sense, ants trying to hear the vibrations of a single grain of sand. And here is the quiet detail that drew so many physicists in. When you do the math of vibrating strings carefully, a particle naturally falls out of the equations that behaves exactly the way a graviton should behave. A graviton is the hoped-for particle that would carry the force of gravity in the same way photons carry light. No one has ever detected one, but in string theory, you do not have to add gravity in by hand. It simply appears, like a note you did not mean to play, but which turns out to belong in the song. For people chasing the unification of physics, this felt like a gentle miracle. Here was a framework that, without being asked, gave you gravity and the quantum world in the same breath. The trouble is that the equations only behave themselves under unusual conditions. The math seems to want more dimensions than the 3 of space and 1 of time that we move through. Some versions ask for 10. Some ask for 11. Where those extra dimensions might be hiding is its own quiet puzzle, one we will sit with in another section. The math also seems to favor a kind of hidden symmetry called supersymmetry, in which every particle we know would have a heavier partner we have not yet found. We have looked for those partners. The great machines that smash particles together at very high energies have searched again and again, and so far the partners have not appeared. This silence is one of the great unresolved tensions in modern physics. It does not prove string theory wrong. The partners could simply be heavier than our machines can reach. But it does mean that one of the theory's quiet expectations has not yet come true. There are other voices in the room. Some researchers think string theory is too flexible to ever be tested, that it can be adjusted to fit almost any outcome, which makes it more a beautiful language than a scientific claim. Others think the framework will eventually narrow itself, the way a wide river narrows as it finds its true channel. Still others have set string theory aside entirely and pursue different paths to quantum gravity, paths we will visit soon. What no one can quite deny is the elegance, the picture of reality as music, of matter as vibration, of the forces of nature as different harmonics of the same underlying thread, has a kind of stillness to it. It suggests that beneath all the noise of the world, the rushing of galaxies, and the spinning of atoms, there might be a single quiet sound. Whether that sound is real or only a dream the math is having remains an open question. The strings, if they hum at a pitch our instruments cannot yet hear. And so we sit with the possibility, the way you sit by a sleeping pond at night, listening for something you are not sure is there. The idea that our universe might hold more than the 3 dimensions we can see did not arrive in a single moment. It grew slowly, in fits and starts, across the early 20th century. The story begins with a quiet German mathematician named Theodor Kaluza, who in 1919 sent a strange letter to Albert Einstein. Kaluza had been playing with the equations of general relativity, the theory that describes gravity as the bending of space and time. He wondered what would happen if he added one more dimension to the math, just to see. The result startled him. When he stretched Einstein's equations into 5 dimensions instead of 4, something unexpected fell out. Alongside gravity, the equations now also described electromagnetism, the force that binds light and magnets and electric charge. 2 forces that had seemed unrelated suddenly looked like 2 faces of the same deeper geometry. It was as if Kaluza had tilted a familiar object and seen a hidden side. Einstein read the letter and was intrigued, though cautious. He sat on the idea for 2 years before helping Kaluza publish it. The puzzle was obvious. If there really was a 5th dimension, where was it? No one had ever bumped into it. No experiment had ever revealed it. The world we live in stubbornly looked 3-dimensional, with time as a 4th thread woven through it. A Swedish physicist named Oskar Klein offered a possible answer in 1926. He suggested that the extra dimension might be real, but rolled up so tightly that no one could notice it. Imagine a long garden hose seen from far away. From a distance, it looks like a thin line, a single dimension stretched across the lawn. Walk closer, and you see that the line is actually a tube with a tiny circular dimension wrapped around its length. An ant crawling on the hose could move along it or around it. A bird flying high above would only see the line. Klein proposed that our universe might be like that hose. The extra dimension could be curled into a circle so small that no measurement of the time could reach it. The combined idea became known as Kaluza-Klein theory, and for a while it seemed like a beautiful hint. Then quantum mechanics rose up in the late 1920s with its strange rules for particles and probabilities, and the Kaluza-Klein dream faded into the background. Physicists had louder mysteries to chase. The idea returned in the 1970s and 1980s, dressed in new clothes. String theorists, looking for a way to make their tiny vibrating threads behave consistently, found that their equations only worked in many more dimensions than 4. Some versions required 10. Others demanded 11. The old Kaluza-Klein trick came back into fashion. The extra dimensions, the theorists argued, must be curled up at scales far smaller than any atom, hidden in folds we cannot probe. But the folds, it turned out, could be shaped in countless ways. The mathematical forms used to describe them, called Calabi-Yau manifolds, are intricate 6-dimensional shapes that twist and loop on themselves. Each shape gives rise to a different version of physics. Some estimates suggest the number of possible shapes runs into the tens or hundreds of digits. This vast collection became known as the string landscape, and it is one reason many physicists remain uneasy about the whole picture. A theory that allows almost any outcome is hard to test. Others have wondered whether the extra dimensions might be larger than Klein imagined. In the late 1990s, a small group of researchers suggested that some hidden dimensions could be as wide as a millimeter. As long as gravity was the only force that leaked into them, this would explain why gravity feels so weak compared to the others. Gravity would be diluted across more space, while the other forces stayed trapped on a thin slice we call our world. Experiments have searched for tiny deviations in how gravity behaves at short distances, looking for the fingerprints of larger hidden dimensions. So far, none have appeared. So the question that Kaluza first asked in his letter remains open more than 100 years later. Are there extra dimensions curled up beyond our reach or stretched out in directions we cannot enter? Or is the appeal of the idea just a mathematical mirage, beautiful on paper, but absent from the universe itself? Some physicists feel certain the dimensions must be there. Others suspect they are clever fiction. The instruments to settle it do not yet exist, and may not exist for generations. For now, the hose stretches out across the lawn, and we cannot tell from where we stand whether it is truly a line or something quietly wrapped around itself, just out of sight. Imagine for a moment that space is not smooth. Picture it instead as a fine fabric woven from countless tiny threads, each one too small to ever see. Pull close enough, and the smoothness dissolves into a kind of mesh. This is the strange idea at the heart of a theory called loop quantum gravity. It suggests that space itself is not a backdrop at all, but a thing made of pieces. The idea begins with a quiet question. If energy comes in small packets, and matter comes in small packets, why should space be any different? Quantum mechanics shows us that almost everything in the small world is grainy. Light arrives in tiny bundles. Electrons live in fixed steps around an atom. So perhaps space, too, has a smallest size, a smallest possible distance below which the question, how far, stops making sense. In loop quantum gravity, that smallest size is built from loops, tiny closed threads of gravitational field, knotted and linked together. Where these loops meet, they form what physicists call spin networks. You can picture them as glowing webs, faintly humming, each junction a quantum of volume, each connection a quantum of area. The smoothness of space, in this view, is an illusion at our scale. Look closer than the Planck length, and the fabric breaks into beads. The Planck length is unimaginably small. It is roughly 100 billion times smaller than a proton. We have no way to measure things at that scale. No microscope could ever see it. No particle we can make is sharp enough to probe it. And yet this is where the loops are thought to live. A hidden architecture beneath everything we touch, everything we are. What makes loop quantum gravity strange is what it does not do. It does not try to unify all the forces into one grand picture. It does not predict new particles or extra dimensions. It only tries to make gravity quantum, to find a version of general relativity that plays nicely with the rules of the small. In that sense, it is humble It asks one question and tries to answer it cleanly. There is another idea in the same family called causal dynamical triangulations. The name is a mouthful, but the picture is simple. Imagine building space-time out of tiny four-dimensional triangles, glued together edge to edge. Then let those triangles flicker and rearrange according to quantum rules, while keeping cause and effect intact. Run the math, and something remarkable seems to happen. At large scales, the jumble of triangles smooths out into the four-dimensional space-time we recognize. At very small scales, something stranger appears. The effective number of dimensions seems to drop, almost as if space becomes thinner as you zoom in. No one is sure what to make of that. It might be a clue about how space is built. It might be an artifact of the math. The result has been seen in more than one approach, which is intriguing. But intrigue is not proof. There is also the asymptotic safety scenario. This one takes a different path. It suggests that gravity, treated as a quantum field, might actually behave itself at very high energies if certain quantities settle into fixed values rather than running off to infinity. In this picture, space stays smooth, but the rules of gravity bend in a way that keeps the math finite. Some calculations support it. Others raise doubts. The verdict is still out. And then there is the boldest thought of all, that space and time might not be fundamental, that they might emerge the way temperature emerges from the jostling of countless molecules. In this view, asking what space is made of is a little like asking what a wave is made of. The wave is real, but it is a pattern in something else. Perhaps space-time is a pattern in some deeper, stranger structure we have not yet named. Each of these ideas paints a different picture of the same hidden world. Loops, lattices, triangles, smooth fields with sharp corners, emergent grids rising from something more abstract. They cannot all be right. They might all be wrong. The honest answer is that we do not yet know whether space is grainy, smooth, woven, or made of something we have not imagined. What we do know is that the question is no longer fanciful. Serious physicists spend their lives chasing it. They write equations that try to count the smallest pieces of the universe, then test those equations against the few clues we have. Slowly, patiently, they look for hints in the cosmic background light, in the shapes of black holes, in tiny shifts of distant photons. The grains, if they exist, leave faint footprints. Whether we will ever find them is itself an open question, drifting quietly through the deep. There is an idea in modern physics so strange that it still surprises the people who study it. The idea is called the holographic principle. It suggests that everything happening inside a region of space might be described in full by information stored on the boundary around that region. Think of a glass sphere. The principle whispers that the whole inside of the sphere, with all its motion and matter, could be written on the thin surface of the glass. This sounds backwards. We live inside a three-dimensional world. We feel depth, distance, volume. Yet the math, in certain carefully chosen settings, keeps pointing in the same odd direction. The story inside the room may be a kind of projection. The real script may be written on the walls. The seed of this idea came from black holes. Researchers found that the amount of information a black hole can hold does not grow with its volume. It grows with the area of its surface. That single fact unsettled a lot of quiet assumptions. If information lives on surfaces, then space itself might be doing something far stranger than we thought. In the late 1990s, a theoretical physicist working in string theory found a precise example of this idea. He showed that a certain kind of universe with gravity inside it could be described exactly by a quantum theory living on its boundary, with no gravity at all. The two descriptions were mathematically equal. Gravity on the inside, pure quantum particles on the outside. Same physics, two languages. This was the first time anyone had seen gravity, and the quantum world speak so cleanly to each other. For decades, the two had refused to share a sentence. Suddenly, in this special setting, they were saying the same thing in different words. The discovery did not solve the unification problem, but it gave physicists their first real bridge between the very large and the very small. The trouble is that the universe described by this bridge is not quite our universe. It has a different shape on the largest scales, a kind of curved, inward-bending geometry. Our universe seems to curve the other way, gently outward, pushed by dark energy. Whether the holographic idea still applies to a cosmos like ours remains an open question. Some researchers believe a version of it must hold. Others suspect we are seeing a mathematical trick that only works in carefully built model worlds. Even so, the idea has begun to connect things that once seemed unrelated. The way information flows in a quantum system, the way space itself seems to weave together out of tiny threads of connection, the way a black hole hides what falls into it, the way galaxies, stars, and light bend along the smooth curves of gravity. All of these may be different notes in the same chord. One striking thread is the link between entanglement and geometry. Entanglement is the quiet bond between two quantum particles, a connection that stays even when they drift apart. Some researchers wonder if the fabric of space is woven from entanglement itself. Pull the threads apart, and space comes undone. Tighten them, and distance forms. In this picture, gravity is not a fundamental force at all. It is a side effect of how information arranges itself. Other researchers disagree. They argue that gravity is its own true thing, deep and irreducible, and that the holographic match is a beautiful coincidence rather than the secret of reality. The debate is alive, and no experiment has yet been able to settle it. The scales involved are far too small, the geometries far too vast. Still, the symphony begins to take shape. A black hole at the center of a galaxy stores information on its horizon. The galaxy itself drifts inside a web of dark matter and dark energy. Light from distant quasars bends along the curves of space-time, carrying news from across billions of years. And underneath it all, if the holographic idea has any truth in it, there may be a quieter layer where these grand scenes are written in tiny patterns of quantum information on some unseen edge. The picture is not finished. We do not know if our universe truly has a boundary in the sense the math requires. We do not know if the holographic language can describe gravity in a cosmos like ours, with its accelerating expansion and its messy, lopsided distribution of matter. We do not know if information is the bedrock, or if something deeper still lies beneath. What we do know is that, for the first time, gravity and the quantum world have been seen humming the same tune, even if only in a single, carefully tuned key. Of all the places in the universe, none has changed our thinking quite like the black hole. For a long time, these dark objects were treated as mathematical curiosities. They lived inside the equations of general relativity, but few thought they truly existed. The idea seemed too strange. A region of space where gravity grew so strong that not even light could escape felt more like a story than a feature of the real cosmos. That view shifted slowly, then all at once. Across the 20th century, evidence built up. Stars were seen orbiting unseen partners with enormous mass. Bright jets of energy poured out of the centers of distant galaxies. By the time astronomers tracked stars whipping around the center of our own Milky Way, the case was nearly closed. Something dark and heavy lived there. In recent years, a network of radio telescopes worked together to capture the soft orange ring of light around one of these objects, a shadow at the heart of a far galaxy. The picture was blurry and warm and very, very still, and it matched the predictions of general relativity to a remarkable degree. For the quest to unify physics, this matters in a deep way. Black holes are the place where Einstein's equations push themselves to the edge of their own meaning. At the center, the math suggests a point of infinite density. Most physicists believe this infinity is not real. It is a sign that the theory has stopped describing nature and started describing its own limits. Somewhere inside, quantum effects must take over, and no one yet knows what those effects look like. This makes black holes the closest thing we have to a laboratory for unified physics. They are places where gravity becomes overwhelming, but also places where the rules of the quantum world cannot be ignored. If a single theory exists that joins the two, it must speak clearly about what happens inside and along the rim and just outside. Our picture of these objects has changed in slow, patient steps. In the 1970s, careful thinking suggested that black holes are not perfectly black after all. They might glow very faintly with a kind of heat that comes from quantum effects near their edge. This soft glow has never been measured directly. It is far too dim against the cold background of space. But the idea reshaped everything. It meant black holes have a temperature. It meant they have entropy, a measure of hidden information. And it meant they slowly evaporate over spans of time longer than the current age of the universe. That last point keeps changing how we think about the cosmos. The biggest black holes today are growing, swallowing gas and dust, and sometimes whole stars. But the universe is expanding, and the supply will not last forever. In a deep future, when galaxies have drifted apart and stars have burned out, these dark giants will begin to shrink. They will give off their faint glow into an emptier and emptier sky. The process will take a number of years so large that the word long seems almost silly. Yet it will happen if our current understanding holds. Inside that slow story sits the central puzzle. When a black hole evaporates, what becomes of everything that fell in? One view holds that the information is somehow carried out in the faint glow, encoded in patterns we do not yet know how to read. Another view holds that information can truly be lost, which would break one of the quietest rules of quantum mechanics. A third possibility is that what fell in never really crossed the edge at all, but smeared itself across the surface in a way we are only beginning to picture. Each of these ideas points at a different shape for the unified theory we are searching for. Right now, the picture is shifting again. New telescopes listen for ripples in space itself, the gentle waves sent out when two black holes spiral together and merge. Each ripple carries clues about the geometry near the edge. Some researchers wonder if small deviations from Einstein's predictions might one day appear in these signals, soft hints of the quantum side of gravity finally showing itself. So far, nature has stayed quiet. The waves match general relativity to the precision we can measure. So our laboratory keeps offering data, and our questions keep growing sharper. The black hole, once an oddity, has become the place where the two great theories of physics are forced to share a room. Whether they will learn to speak the same language there, or whether something stranger will be needed remains an open question. For tonight, it is enough to picture that quiet, glowing ring suspended in the dark. Light is how the universe tells us most of what we know. It carries the heat of distant suns across cold space. It bends around galaxies. It paints the soft pinks and greens of nebulae, the pale gold of old starlight, the deep red of clouds still warm from ancient birth. And yet, when light falls into a black hole, it seems to take its story with it. The puzzle of what happens to that story is one of the deepest unresolved questions in physics. To begin, picture a single photon drifting through space. It carries a tiny pattern of information, like a small letter in the universe's long sentence. The color tells us where it came from. The angle tells us when it bent. The number of photons in a beam can describe a star's surface, a planet's air, a swirl of dust around a young sun. Every glow you have ever seen is a kind of message written in light. Now picture that photon falling toward a black hole. It crosses the invisible edge, the event horizon, and it does not come back. According to general relativity, that is the end of the matter. The light is gone, the message is gone, and only a slightly larger black hole remains, smooth and silent. But quantum mechanics has a different rule, and that rule is strict. Information, in the quantum sense, can never be truly destroyed. The fine pattern of a system, no matter how scrambled, must in principle survive. Burn a book and the information is still there, hidden in smoke and ash and the faint glow of heat. In theory, a careful enough observer could read the book back out of the embers. Quantum mechanics insists on this. So the question becomes very simple and very hard. When light falls into a black hole, where does its information go? For many years, one possibility seemed to be that the information was simply lost. The black hole ate it, and that was that. But this idea breaks one of the firmest rules of the quantum world, and most physicists became unwilling to accept it. A different possibility took shape. Perhaps the information slowly leaks back out as the black hole glows. That glow is called Hawking radiation. The idea is that black holes are not perfectly dark. They give off a faint, slow whisper of particles a kind of soft thermal light, and over enormous spans of time, they shrink and eventually fade. If the information of everything that fell in is somehow encoded in that faint outgoing light, then nothing is truly lost. The book is read back out, one dim photon at a time. That sounds tidy, but it is far from settled. The math of how the information would get out is strange and contested. Some researchers wonder if the outgoing radiation carries hidden correlations, tiny patterns that store the memory of everything that ever fell in. Others wonder if the horizon itself is not as smooth as relativity suggests, and that something more violent waits there, a kind of bright shell wherein falling things are recorded before they cross. Other thinkers prefer the idea that the inside and the outside of a black hole are secretly the same place, two views of one underlying pattern. So the information was never really separated from us at all. Each of these pictures clashes gently with the others. Each one solves part of the puzzle and breaks part of it. The question of which, if any, is right remains open. What makes this so important for the dream of unifying physics is that the answer would tell us how the smooth world of gravity and the grainy world of quantum rules truly fit together. Light, in this story, is the thin thread that connects the two. The way light enters a black hole is described by relativity. The way light carries information is described by quantum mechanics. The way light might escape, slowly and softly, depends on a deeper theory we do not yet have. So when you imagine a black hole now, do not picture only darkness. Picture a faint, slow shimmer at its edge. Picture light folded inward, light radiating outward across ages longer than the present age of the universe. Picture a glow so dim that no telescope yet built could see it. And yet inside that glow may be the record of every star, and stone the black hole ever swallowed. Whether that record really exists, and whether we could ever read it, is part of what physicists hope a unified theory will finally tell us. For now, the message at the edge waits, bright in principle, invisible in practice, patient. If you could press your ear against the fabric of space itself, what would you hear? This is the strange invitation at the heart of quantum gravity, the long search for a theory that weaves the tiny world of particles together with the wide, curving world of gravity. Space does not carry sound the way air does. There is no hum, no whisper, no soft static between the stars. And yet, in another sense, the universe is full of vibration. Gravitational waves ripple outward when black holes collide. Magnetic fields around planets sing in low tones when spacecraft translate them into audio. The solar wind, that thin stream of charged particles flowing from the sun, hisses softly when its data is turned into sound we can hear. The cosmos is quieter than any room you have ever sat in, and louder than you might guess. Quantum gravity asks whether space, at the smallest possible scale, also has a kind of music. Not sound in the everyday sense, but vibration, pulsing, a trembling that we cannot yet measure. The idea grows from a simple problem. General relativity treats space and time as a smooth sheet that bends under the weight of matter. Quantum mechanics treats everything else as restless, jittery, full of tiny flickers of probability. When you push these two descriptions together at very small scales, the math begins to break. Some researchers think this means space itself must flicker too. That, at scales far below an atom, the smooth sheet dissolves into something grainy, foamy, alive with motion. One name for this idea is space-time foam. It is only a picture, not a confirmed truth. In this view, what looks like empty calm at our scale is, deep down, a constant froth of geometry bubbling in and out of existence. If you could shrink small enough, the floor beneath your feet would no longer be a floor. It would be a churning sea of tiny shapes, forming and unforming faster than any clock could count. Some theorists wonder whether this foam leaves a faint signature on light that travels across the universe for billions of years, smearing it ever so slightly. So far, careful searches have not found that smearing. The foam, if it exists, hides well. A competing picture comes from loop quantum gravity. Here, space is not foam, but a fine network, a kind of woven mesh of tiny loops linked at every point. The mesh has a smallest size, below which the word distance stops meaning anything. In this view, the universe is more like a fabric than a fluid. Each thread carries a small unit of area or volume, and the threads connect into a vast, quiet web. Other researchers prefer yet another picture called causal dynamical triangulations, in which space is built from tiny triangle-like pieces that arrange themselves over time. None of these ideas has been proven. Each makes the same promise: to gently stitch gravity into the quantum world, and each tells a different story about what the stitching looks like. The sound, if there is one, would come from how these tiny pieces move. In loop gravity, the network can change, with loops splitting and joining in slow patterns. In triangulation models, the small shapes rearrange in steady steps. In string theory, every particle is a tiny vibrating thread, and the note it plays determines what kind of particle it is. An electron is one note. A photon is another. Gravity itself, in this view, is just one more song in a wider symphony that no instrument has yet heard. The trouble is, the strings would be so small that no experiment we know how to build could detect them directly. What we can listen for instead are echoes. When two black holes spiral together, the gravitational waves they release carry information about the geometry near their edges. If space is truly grainy at the smallest scales, perhaps something about that graininess shows up in the final ringing tones of the merged black hole. Detectors on Earth have begun to catch these tones with growing clarity. So far, they match the predictions of plain general relativity. The quantum whisper, if it is there, stays below the noise. Some researchers find this discouraging. Others find it useful. Every clean measurement narrows the space where new physics can hide. For tonight, picture the universe as a vast, quiet instrument, tuned in ways we do not yet understand. Somewhere beneath the silence, something may be humming, a song written in a language of geometry and probability we have only begun to spell out. Whether we ever learn to hear, it is still an open question. The listening continues slowly, patiently, across decades and across the sky. There is a strange kind of beauty in how the night sky obeys arithmetic. A planet circles its star, and we can write down where it will be 1,000 years from now. almost to the second. A moon rises on a distant world, and the same equations that lift the tide on Earth predict its shadow on alien sand. The universe seems to run on a small handful of simple rules, written in the clean language of numbers. And yet, when we try to weigh the galaxies, the numbers begin to disagree with what we see. The trouble is gentle at first. A spiral galaxy spins, and its outer stars should drift more slowly than its inner ones, just as the outer planets of our own system move more slowly than the inner ones. That pattern is one of those quiet rules, written long ago by Kepler and refined by Newton. Inner stars whip around quickly. Outer stars should lag. The math is elegant, and it has held true for centuries inside our own neighborhood. But out in the great pinwheels of distant galaxies, the outer stars do not lag. They keep pace. They move as if held by some invisible scaffolding, as if the galaxy were heavier than its glowing parts can explain. The equations are not broken. The stars are simply behaving as though there is more mass present than any telescope has ever seen. 5 times more by most careful counts. For every gram of ordinary matter, there seems to be roughly 5 grams of something else. That something else is what we call dark matter. The name is honest. It tells you only what it does not do. It does not shine. It does not absorb light. It does not glow in the warm infrared or whisper in the radio bands. It only pulls. And it pulls with such steady precision that the rotation curves of galaxies, the bending of light around clusters, and the faint ripples in the early universe all line up with the same hidden weight. The math of this is, in its way, lovely. The same gravitational equations that guide a comet around the sun, when applied to a whole galaxy, produce a clean prediction. Plug in the visible stars and gas, and the answer comes out wrong by a known factor. Plug in 5 extra parts of unseen mass for every one we can see, and the answer snaps into place. Across thousands of galaxies, the ratio holds with a quiet stubbornness. The universe seems to be following a simple recipe. We just cannot find one of the ingredients. Theories for what dark matter might be have come and gone like seasons. One long-standing idea proposes a heavy, sluggish particle that barely speaks to light or to ordinary matter. Decades of careful experiments, buried deep underground to shield them from cosmic noise, have searched for the faint nudge of such a particle passing through. So far, the detectors have stayed quiet. Another idea suggests something much lighter, almost ghostly, drifting like a soft fog through every room. A third proposes that dark matter is not matter at all, but a sign that our equations of gravity need a small correction at very large distances. Each of these ideas carries its own arithmetic. Each makes slightly different predictions about how galaxies should cluster, how light should bend, how the cold echo of the Big Bang should ripple. And here is where the limits of our models begin to show. The numbers that describe ordinary matter are crisp and well tested. The numbers that describe this hidden 5/6 of the cosmos are sketches, written in pencil, waiting for an experiment to ink them in. The quest to unify physics watches all of this with great interest. Any complete theory, one that ties gravity to the quantum world, would need to say something about dark matter. It would need to explain why the cosmos seems to lean so heavily on something we cannot yet name. Some versions of string theory predict whole families of unseen particles that could fit the role. Some versions of modified gravity sidestep the problem by changing the equations themselves. Both approaches are mathematically beautiful. Both remain incomplete. Neither has yet earned the quiet authority of a confirmed law, so the elegant numbers continue their work. Orbits stay predictable. Galaxies keep spinning at their strange, steady rates. The ratio of seen to unseen mass holds across the sky like a signature we cannot read. Somewhere in that signature, perhaps, is a hint about how the very large and the very small finally fit together. For now, the math points clearly at a missing piece, and the universe waits, patient as ever, for us to discover what it is. There is a number that physicists carry with them like a small stone in the pocket. They turn it over in the dark, examine it in the light, and still cannot explain it. The number describes how much the empty space of the universe seems to push outward. It is very small, and the smallness is the problem. In the late 1990s, two teams of astronomers studied the light of distant exploding stars. They expected to find a universe whose expansion was slowing down, gently pulled back by all the matter inside it. Instead, they found the opposite. The galaxies were drifting apart faster and faster, as if some quiet pressure were pressing the sky open from within. We now call that pressure dark energy. We do not know what it is. One natural guess is that dark energy is the energy of empty space itself. Even a perfect vacuum in quantum theory is never truly still. It hums with tiny fluctuations, particles flickering in and out of being. When physicists try to add up all that quiet humming, they get a number. Then they compare it to the gentle push astronomers actually measure. The two numbers do not match. They miss each other by a factor so vast it has become a kind of legend in the field, sometimes described as the worst prediction in the history of physics. So one possibility is that the vacuum does carry an energy, but some unknown rule cancels almost all of it, leaving only the faintest trace behind. That trace would be what we see. The trouble is, no one has found the rule. The cancellation would have to be precise to many, many decimal places, like balancing a pencil on its tip for the entire age of the cosmos. Some researchers wonder whether such fine balance can really be an accident. Another idea takes a different path. Perhaps dark energy is not the energy of empty space at all. Perhaps it is a new field that fills the universe, slowly changing as time passes. This field is sometimes called quintessence, a soft name borrowed from old philosophy. If quintessence is real, then the push of the sky might not be perfectly steady. It might drift ever so slightly over billions of years. Telescopes are now searching for that drift. So far, the sky looks steady, but the measurements are not yet sharp enough to settle the matter. A third view goes further still. Maybe dark energy is a sign that our theory of gravity is incomplete on the largest scales. General relativity works beautifully across the solar system, across galaxies, across the gentle bending of starlight. But the whole universe is something else. Some thinkers wonder whether gravity, stretched across billions of light years, behaves in ways Einstein's equations do not quite capture? If so, dark energy would not be a substance at all. It would be a hint that we are reading the cosmos with the wrong glasses. Each of these ideas has its own weakness. A true vacuum energy demands a cancellation no one can explain. A drifting field demands a particle no one has detected. A modified gravity demands changes to equations that have passed every other test we have ever thrown at them. None of the three has yet pulled ahead. What makes the puzzle so striking is how delicate the balance seems to be. If dark energy were much stronger, galaxies could never have formed. Matter would have been swept apart before it could gather, and the night sky would be empty of any structure to look at. If dark energy were much weaker, or if it pulled inward instead of pushing out, the universe might have collapsed back on itself long ago, before stars had time to cook the elements our bodies are made of. The value we measure sits in a narrow window where stars, planets, and patient observers can exist. Some take this as a clue that many universes exist, each with its own value, and we naturally find ourselves in one of the rare ones where life is possible. Others find that answer unsatisfying, a kind of shrug in mathematical clothing. They suspect a deeper rule is waiting, one that will make the small number feel inevitable rather than lucky. For a unified theory, dark energy is a quiet test. Any final equation of gravity and the quantum world will have to explain not only black holes and particles, but also this faint outward pressure and the strange softness of its value. Until then, the sky keeps drifting apart at its gentle, unexplained rate. And somewhere in that drift, a clue is waiting, patient as starlight, for someone to notice what it has been saying all along. Somewhere along the long road toward unifying physics, a strange question begins to surface. If our universe arose from a quantum field, from a brief moment of expansion, from a balance of forces that could have tipped 1,000 ways, then why did it settle into this particular shape? Why these forces, these masses, these constants? And if the math allows other shapes, do those other shapes exist somewhere, in some way we cannot reach? This is the multiverse question, and it sits like a quiet shadow at the edge of every attempt to write a final theory. The idea takes several forms, and each one comes from a different corner of physics. One version grows out of string theory. The equations of strings, as we have seen, do not pin down a single universe. They allow a vast collection of possible solutions, sometimes called the string landscape. Each solution describes a universe with its own laws, its own particles, its own version of gravity. If all of these solutions are real, then our cosmos may be only one valley in an enormous mathematical terrain. A second version comes from inflation, the brief burst of expansion thought to have stretched the early universe smooth. Some inflation models suggest that the expansion never fully stopped everywhere. In certain regions, space keeps inflating, budding off new pockets, each one cooling into its own little cosmos. This picture is called eternal inflation, and in it, our observable universe is one bubble among countless others, drifting in a foam we will never see. A third version comes from quantum mechanics itself. In the many worlds interpretation, every quantum choice splits reality into branches, each one as real as the last. The cat is alive in one branch and still in another. Galaxies form one way here and another way there. The branches do not interact. They simply exist side by side in a structure too vast to picture. These three multiverses are not the same idea. They come from different equations and answer different puzzles. Yet, they share a common feature. None of them so far can be tested in the usual way. We cannot send a probe to another bubble. We cannot peek into another branch. We can only ask whether the math that predicts them is the math that also describes our world. This is where the disagreement grows sharp. Some physicists argue that a multiverse is a natural consequence of theories we already take seriously, and that dismissing it is a kind of stubbornness. If inflation is real, eternal inflation may follow. If string theory is real, the landscape may follow. To them, the multiverse is not a wild guess. It is the quiet implication of equations that have done good work elsewhere. Other physicists push back, gently but firmly. A theory that cannot be tested, they say, sits uneasily inside science. If every possible outcome happens somewhere, then no observation can rule the theory out. And if no observation can rule it out, then it may not be helping us understand our own cosmos. Better, they argue, to keep searching for a deeper principle that explains why our universe took this form without invoking infinite others. There is a softer middle path as well. Some researchers wonder whether the multiverse might be tested indirectly. If two bubble universes ever collided in the distant past, perhaps a faint mark would remain in the cosmic microwave background, the leftover glow of the early sky. Searches for such marks have so far come up empty. The absence is not proof of anything. It is simply a quiet result, waiting for more data and better eyes. The multiverse question also touches the unification dream in an uncomfortable way. If a final theory predicts not one universe, but a forest of them, then the dream changes shape. The single equation we hoped to find may not pick out our world. It may only describe the rules of the forest, leaving the choice of any one tree to chance, or to selection, or to something we have not yet named. For tonight, it is enough to hold the picture loosely. Imagine our cosmos as a single pale bubble drifting in a darkness we cannot map. Around it, in directions that are not quite directions, other bubbles may shimmer with their own stars and their own laws, or there may be nothing at all beyond our horizon, and the bubble may be the whole of what is. Both pictures are allowed by the math we have. Neither is proven. The quest to unify physics may, in the end, tell us which picture is closer to true. Or it may leave the question open, a soft riddle at the edge of every equation, waiting for minds not yet born to wonder at it in turn. Of all the puzzles in the quest to unify physics, perhaps the strangest sits hidden inside something we feel every moment we are awake. Time. We treat it as the steady backdrop of our lives. The clock ticks, the kettle boils, the night passes. Yet, when physicists look closely at their deepest equations, time begins to act in ways that do not match the simple feeling of a moment slipping by. In Einstein's picture of gravity, time is woven into space itself. It bends near heavy things. It slows near black holes. It runs a little faster on a mountain than at sea level. Clocks on satellites tick at a slightly different rate than clocks on the ground, and engineers must correct for this every day. So time is not a fixed river. It is part of the shape of the universe, stretching and bending with the matter inside it. In the quantum world, time looks very different. There, time is more like a steady metronome, ticking outside the equations rather than woven inside them. Particles change, waves spread, probabilities shift, but the time variable itself sits apart, untouched, as if handed down from some clock outside the system. Two of our finest theories, two completely different roles for time, and no one is sure which picture is closer to the truth. When physicists try to combine gravity with the quantum world, this disagreement becomes a serious problem. One famous attempt to write down a quantum equation for the whole universe ends with something startling. The equation has no time in it at all. The variable simply drops out. Some researchers take this as a deep clue. They wonder whether time, at the most basic level, is not a fundamental thing. It might be something that emerges, like temperature, only when many smaller pieces come together. Others find this idea hard to accept. Time feels too real, too central, too tied to cause and effect to be a kind of illusion. One competing view holds that time is fundamental, and that our quantum equations are simply incomplete. In this view, a finished theory of everything would put time back where it belongs, perhaps in a form we have not yet imagined. Both camps are working. Neither has won. The question remains open. If you stretch your mind forward, the strangeness only grows. Imagine 1,000,000 years from now. Our species, if it still exists, may have spread far from this small blue world. The constellations we know will have shifted because stars drift slowly across the sky. Familiar patterns will soften and rearrange. Some of the questions we ask tonight may have answers. Others may have been replaced by deeper questions we cannot yet form. Push further. 1,000,000,000 years from now, the sun will have grown brighter and hotter. The oceans here may have boiled away long before. Continents will have collided and broken apart again. New mountains will rise where deserts now lie. The Andromeda galaxy drifting toward us at a slow cosmic pace, will be tangled with our own Milky Way, their stars sliding past each other in a long, gentle merger. Through all of this, the puzzle of time may still sit unsolved on someone's desk, in some form we cannot picture. Further still, trillions of years out, the stars themselves begin to fade. The bright ones burn out first. Smaller, redder stars linger far longer, glowing patiently in a darkening sky. New stars form less and less often because the gas needed to make them grows thin. Galaxies drift apart, carried by the slow stretching of space. The night sky, if anyone is left to look, becomes quieter and emptier. And yet, even in that long dimming, new things form. Black holes grow and slowly evaporate over spans of time, so vast they barely fit on a page. Strange, cold objects gather. Whatever physics is, it keeps working in the dark. Time, however we end up defining it, keeps doing whatever it does. This is the gentle hope inside the question. A finished theory of unification, if one is ever found, would have to explain not just space and matter and force, but also this most ordinary and most mysterious thing. Why time flows in one direction, why the past feels fixed and the future feels open, why we remember yesterday and not tomorrow. None of that is fully understood even now. So as you rest, let the thought settle softly. The universe is always becoming something new. Stars are forming somewhere tonight. Others are quietly going out. And the small, stubborn question of what time really is waits patiently, unanswered, for minds that have not yet been born. Step back for a moment and picture the whole of it. The patient work of building a single equation for everything is not happening in some quiet library at the edge of the world. It is happening inside us, around us, in machines buried under mountains, in telescopes drifting above the atmosphere, in tunnels of cold metal where particles race each other at nearly the speed of light. The search for a unified theory is a search that uses the entire planet as its laboratory, and in a strange and lovely way, the universe is helping us look. Think of the great ring beneath the border of France and Switzerland, where protons circle a track many miles long. Inside that ring beams of particles meet head-on, and for the briefest instant, the conditions resemble the young, hot universe just after its beginning. Physicists watch the wreckage of these collisions, hoping to glimpse something new. So far, the deepest theories of unification, strings, extra dimensions, supersymmetry, have not shown themselves there. Some researchers wonder whether the answers lie just beyond the energies we can reach. Others wonder whether we have been looking in the wrong direction entirely. There are quieter laboratories too, deep underground in old mines repurposed for science. Vats of liquid xenon sit in perfect stillness, waiting for a single dark matter particle to bump into a single atom. Years pass with no signal. The silence itself is data. It tells us gently that whatever dark matter is, it is shyer than we guessed. The theories must adjust. The equations must stretch. The search continues. Above us, telescopes listen for the faint hum of the early universe. The cosmic microwave background, the soft afterglow of the first light, carries patterns that may hold the fingerprints of quantum gravity. If space itself is made of tiny grains, or if it once vibrated like a string, those patterns might whisper of it. Some researchers believe the signal is hidden in the polarization of that ancient light. Others suspect the signal may be too faint to ever separate from the noise. Both camps keep looking. Then there are the gravitational wave detectors, long arms of laser light tuned to feel the gentle stretching of space when distant black holes collide. Each ripple that arrives at Earth carries information about gravity in its rawest form. One day, a ripple may arrive that does not match what general relativity predicts. That small mismatch, if it ever comes, could be the first true crack in the old equations, the first hint of the deeper theory beneath them. And here is the part worth holding as you drift. You are not separate from any of this. The calcium in your bones was forged inside ancient stars that lived and died before the sun was born. The iron in your blood was cooked in the cores of those stars and scattered across space when they collapsed. The hydrogen in every cup of water on Earth has been adrift in the cosmos for nearly 14 billion years. You are, quite literally, a small arrangement of stardust that has learned to ask questions about itself. The quest to unify physics is the universe trying to understand its own rules, using pieces of itself as the instruments. The telescopes are made of atoms. The detectors are made of atoms. The physicists are made of atoms. The equations are written by minds that emerged, somehow, from the same quiet processes that lit the first stars. It is a strange loop, soft and beautiful, and we do not fully understand how it came to be. Maybe the final theory will arrive in a clean burst of insight, the way light from a distant supernova arrives all at once after traveling for ages. Maybe it will arrive piece by piece, a slow assembly of small confirmations over a century. Maybe it will not arrive at all in any form we would recognize, and our descendants will look back at our equations the way we look back at older maps of the world, with affection for how much they got right and how much they could not yet see. The honest truth is that nobody knows which of these futures we are living in. The experiments continue. The theories continue. The patient watching continues. And the universe, vast and quiet and full of unfinished business, keeps offering small clues to anyone willing to look closely. You are part of that looking, even now, even half asleep. Your curiosity is itself a tiny instrument of the cosmos. The atoms inside you came from places you will never see, and they have arranged themselves for a little while into something that wonders. That alone is one of the strangest and most beautiful facts in any theory we have yet imagined. We have come a long way together, you and I, through the great unfinished question of physics. We have looked at the very small and the very large. We have watched gravity refuse to sit beside the quantum world. We have heard about strings that might hum beneath reality, and loops that might weave space itself from tiny grains. We have stood at the edge of black holes and listened for whispers of information returning from the dark. And through it all, one truth has stayed soft and steady. We do not yet know how the pieces fit. That is a beautiful thing to carry into sleep. The mystery is not broken. It is open. Somewhere tonight, a researcher is writing equations in a quiet office. Somewhere else, a student is reading a paper for the first time, and feeling their mind tilt with wonder. The question is alive in many minds at once, passed gently from one generation to the next, like a candle moved carefully from room to room. It is possible the answer will arrive in our lifetime. A clever experiment, a fresh idea, a young thinker who sees what others have missed. It is also possible the answer will take centuries. The deepest questions tend to keep their secrets longer than we expect. The people who first wondered why the stars shine did not live to see the answer. They wondered anyway. They looked up anyway, and the wondering was its own kind of gift. Picture, for a moment, a small blue planet turning slowly in the dark. Its oceans rest under a pale moon. Clouds drift across continents. Somewhere on the night side, a soft wind moves through tall grass. The planet does not know it is the home of beings who ask impossible questions. It simply turns, as it has turned for billions of years, held by the quiet pull of its star. Now picture the star itself, a warm yellow ember among countless others, and the galaxy around it, a slow wheel of light, taking 200 million years to make a single turn. And beyond that galaxy, the soft glow of others, scattered like lanterns across a vast dark sea. The universe is enormous beyond easy thought, and yet it is also gentle. It moves slowly. It gives us time. Somewhere in that great slow turning, the laws of physics are doing their quiet work. Gravity is bending space around every mass. Quantum fields are shimmering through every empty corner. The two great pillars hold up the same sky, even though we cannot yet see how they meet. Maybe they meet in a way we have already half-guessed. Maybe they meet in a way no one has imagined. The not knowing is not a wound. It is a doorway. You can rest in that doorway tonight. You do not need to solve anything. You do not need to choose between strings and loops, between extra dimensions and grains of space, between a single universe and many. You only need to know that the question is being carried gently by many hands, and that the universe, whatever its deepest equations turn out to be, has been kind enough to make a place where such questions can be asked at all. Soft light on water, the hush of a forest at night, the slow breath of a sleeping world. The same physics that puzzles our finest minds, also rocks the tides, also lights the stars, also holds the warmth in a quiet room. Whatever the final theory looks like, it already surrounds you. You have been inside it your whole life. You are inside it now. Let the questions drift. Let the theories settle like snow. Let the equations rest on their distant chalkboards while you rest here. The black holes will still be turning in the morning. The galaxies will still be drifting. The mystery will still be open, patient as ever, waiting for whoever comes next. Maybe one of those who comes next is dreaming tonight. Maybe it is a child who has not yet learned the word gravity. Maybe it is you, on some quiet evening years from now, when a small idea arrives that no one else has had. The universe is generous with its puzzles. It seems to want to be understood slowly, gently, across many lifetimes. For tonight, you have done enough. You have wondered well. You have looked into the deep and let the deep look back softly, without fear. Close your eyes now, if they are not already closed. The great wheel turns. The stars hold their light. The question waits kindly for another day. Subscribe for a brand new space topic every night. One tap, and something incredible is waiting for you tomorrow. Sweet dreams.